Welcome back to the video playlist on dynamic programming. So in this video we're going to talk about when you can use dynamic programming to solve a problem. Not all optimization problems can be solved with dynamic programming. In the last video we talked about how you have to have certain repeating work, and that can be referred to as overlapping subproblems. So if one part of the solution tree that you would be exploring is basically identical to another part of the solution tree that you would be exploring, then we don't want to duplicate the work, and dynamic programming will help us out. However, just having overlapping subproblems is not sufficient. In addition to that, we need to have optimal substructure. And what that means is that the solution to a large problem is created from optimal solutions to smaller problems. And to help illustrate this, I'm going to begin with the first problem that we'll look at, which is a rod cutting problem. Okay, so the idea here is you manufacture metal rods, and our metal rods look like that. And you can cut your rods at various unit intervals. And you don't have to cut it at all, but of course you're in business, so what you want to do is maximize the total sale for what you can get for this particular piece of metal. And that will depend upon what the market values are currently for chunks of metal of certain length. So how many pieces did I put here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Actually, let's go ahead and let's just shrink this by 1 because I'm really happy with 10. Okay, so here we have a rod of length 10. In general, this will be of length n. And we also have a pricing table for this. So items of a rod of length 1 might sell for $1, one whatever. Rod of length 2 might sell for 3. Rod of length 3 might sell for 3. Rod of length 4 sells for 5. 5 will also sell for 5. 6 sells for 7 units. 7 sells for 8 units. For some reason, no one wants rods of length 8, and they only sell for 3 units. Rods of length 9 can sell for 10, and rods of length 10 also sell for 10. Okay, so this is basically a lookup table for if we were to cut things into this length, how much money we could get for them, and our goal would be to maximize what we can sell this for. So if we don't cut it at all, we can get $10 for it. However, that's clearly not optimal because I could cut it into something of length 9 and something of length 1 and get $11 for it. Can we do better than that? It's not immediately clear to me that with this that I can do better than that, but I want to be able to write an algorithm to solve this. Okay. Now, I said that in order to use dynamic programming, our problem has to have optimal substructure to it. So does this problem have optimal substructure? And really what we're saying there is if I had when I want to find out if there is what the optimal solution is for 10, that means the optimal solution for 10 somehow includes the optimal solutions for 9, possibly 9 or 8, 9, 8, 7. But the things that are smaller than this, the optimal solutions for those can be combined with maybe just a little bit more data to give me 10. And it turns out that is the case here. Because if I know the optimal solutions to all of these smaller values, well, I know that for 10, it could be just don't cut it at all, Or it could be what I get for this 1 plus what I got as the optimal for 9. I don't have to recalculate the optimal for 9 here because what I got as optimal for 9 will still be optimal as a sub-piece of 10. Or I could take 2 of these plus what was optimal for 8, take 3 of them plus what was optimal for 7, etc. So if I build up a solution from the small end, I can make it so that I don't duplicate any work here. So if I want to use dynamic programming to solve a problem, I wind up having to take kind of 4 steps in this. The first one is define what the optimal solution would look like. Okay, what is it that that we're actually trying to solve for here? Second, I want to actually write the recurrence relationship. Okay. And in fact, we could even write the recursive function out mathematically. Okay. So while we're not going to code a recursive solution in dynamic programming, that's what we're trying to avoid here, we're actually going to write a recursive solution just so that we can use that mathematically to help us figure out what we're doing. Then we fill in a table from bottom up. And as I showed with the Fibonacci sequence, generally your recursive functions work top down. So you call the recursive function, you say, I have a bar of length 10, what is optimal for this? And then it works its way down to size 1 or 0, whatever you have as your base case. With dynamic programming, you start at the bottom and you work your way up, and the whole optimal substructure guarantees that you can look up values earlier in the table and use that to solve. And then optionally, you can use the table that you've built to build the optimal solution itself. So going back to that maze problem, when I write a function that solves for the shortest length path in a maze, generally I have it return me an int. Okay? And so it tells me how many steps there are in the optimal solution, but it doesn't give me back the optimal solution. And you can make the recursive version do that, but it takes a bit of work and finagling to do it. It turns out that with dynamic programming, when you fill in this table, the table itself contains sufficient information for you to go back and build an optimal solution. And so you can figure out what the optimal solution looked like from that. So we'll come back to this in the next video, and we'll actually apply these 4 steps to solving the rod cutting problem.